Okay, well, we can just get started. So it's our pleasure to have Hank Morris from UIC, and he'll be talking about isomonodromic deformations of flat bundles and Codimension of Hodge.
All right, yeah, thank you for the introduction. Thanks for the invitation and everyone for coming. So the way I want to start is by pointing out that one of the things that's very special in algebraic geometry is that the objects we study, algebraic varieties, often get parameterized by spaces that are also algebraic varieties. And even more so, a lot of the gadgets that we attach to varieties when we study them, they have parameter spaces, and those also have the structure of varieties or things close to them. So two examples of that are that if I have a curve of genus G, then we can associate to this class of objects the moduli space of genus G curves, which is MG. One of the things that we like to study on varieties are vector bundles on them. And there's an enriched class of vector bundles that are called flat vector bundles. So these are vector bundles with a flat connection. So that's a map from E to one form's value in E, satisfying this flatness condition. Where it's 0, there's a Leibniz rule for how you actually write out what this does. So I can look at a flat vector bundle of rank R, let's say. So once you have two objects that both vary in moduli, a natural question that you can ask is, well, how do both of these vary? Can you vary these at the same time in moduli? And the answer to that is yes. There's a moduli space due to Simpson called the Rham moduli space. So let me write C for the universal curve, and C over mg. There's this Rham moduli space, which is called the relative Rham moduli space, and it parameterizes essentially these pairs of curves together with a flat vector bundle. And today I kind of want to talk about some of the interesting geometry of this space. So the geometry of this space, going back to Simpson's construction, is very much informed by the non-abelian Hodge correspondence. So in order to pose the questions that I want to ask and answer, I should first tell you a little about what goes into that. So let me just review that briefly. So the non-abelian Hodge correspondence. Okay. So there is one object at play that we've already seen, which are these flat vector bundles of any variety. And going back to Riemann and Hilbert, these are known to be equivalent to representations of the fundamental group of my variety. And I should maybe say semi-simple representations. And this is called the Riemann-Hilbert correspondence. And the third ingredient in this that makes this the non-abelian Hodge correspondence is that these flat vector bundles have another object corresponding to them called Higgs bundles. So let me briefly tell you what a Higgs bundle is. So a Higgs bundle is a holomorphic vector bundle E on my curve, and it's going to have a endomorphism value of 1 form. So with a one form theta. That you can kind of think of as a degeneration of the connection. The condition that this theta is going to satisfy, it's going to satisfy a similar condition to this flatness. It's going to satisfy this so-called integrability condition. The bracket with itself is equal to 0. Okay. So really, to state the non-abelian Hodge correspondence precisely, I should specify that these are polystable degree 0 Higgs bundles. So polystable is going to mean that it's a direct sum of stable objects. Stable objects, there's this notion of slope, the degree divided by the rank. And stability says that any proper subbundle has to have strictly smaller slope. Okay. So one way to think about the non-abelian Hodge correspondence is that an analogy with one of the first definitions of cohomology that you might learn, you should view this object as kind of being like an H1 of your object with coefficients in general linear with non-abelian coefficients. And so just as the Hodge decomposition and Hodge classes and this whole package that you get with Hodge decomposition on H1 with complex coefficients, this correspondence and some of the structure that it has is going to be the non-abelian Hodge structure on this object. Of course, what is that structure in addition to this correspondence? Well, there's a very special class of flat vector bundles that we have. And these are the flat vector bundles that underlie a variation of Hodge structure. And so maybe the natural space to say that these live in is in this Higgs bundle world. Let me briefly tell you what a variation of Hodge structure is. So the definition, again. A polarizable complex variation of Hodge structure. Well, it's one of these objects, and you can view it as a flat vector bundle with a decomposition into smooth subbundles, which I'll call PQ, satisfying Griffith's transversality. Griffith's transversality. So what is Griffith's transversality? Well, I have this connection nabla, and on a BPQ piece, the connection will actually decompose into quite a few parts, but yeah, maybe I should say. The connection is going to decompose into 4 different operators, and so there's 4 possible places that this VPQ piece can land, which you have VPQ tensor 1,0 forms, VPQ tensor 0,1 forms, the P-1, P+1 tensor 1,0 forms, and P+1 Q-1 forms. 0, 1. So that's a complex variation of Hodge structure. The polarizable condition is that plus there is a flat Hermitian form. on the bundle, psi, times v of c, so that it makes each of these pieces actually orthogonal with respect to this formula. So the PQ and the P prime P prime are orthogonal for the P prime different. And then there's a positivity condition. So I mentioned that these variations of Hodge structure live naturally in this world of Higgs bundles. Also, in the world of representations of the fundamental group, there's a sort of distinguished class, which is that these representations are valued in GLRC, but a distinguished class are those representations that are integer valued. And the combination of the two of those, you pair those together, you would get a variation of Hodge structure such that the corresponding representation is integer valued. And that is a Z variation of Hodge structure. And these are the analog of Hodge classes within this non-abelian Hodge structure. But again, one lives in here, the other lives in here. And so the place that we want to consider these Hodge classes, these Z variations of Hodge structure, is in here, which kind of connects these two objects. So I'll give that a name. The non-abelian Hodge locus in the Rham space is the set of Z variations of structure. Yeah. And what I want to talk about is kind of the geometry of this locus. Any questions so far? And about the big dump of definitions. So the geometry of this object is pretty mysterious. We know that it's perhaps a countable union of algebraic subvarieties in the compact case, and the non-compact case less is known. And the main thing I want to kind of inform you about is a definition or a notion of the dimension of these objects. So these as representations have integer values. And that means that there's kind of a rigidity property to them, in the sense that, well, if you perturb an integer, you no longer have an integer. So if I want to look at the geometry of this locus, well, inside of this relative moduli space, there are directions I can move that are going to deform the curve, and there's directions I can move in that are going to deform the corresponding flat vector bundle. And if I deform that vector bundle or the representation, I'm going to leave that Hodge locus because I'm no longer going to be integer valued. So if you want to study the geometry of this locus, you actually have to study a particular locus within this, which is that you have to keep the corresponding monodromy representation the same. You can only vary the curve. And so that sort of direction you can move is called the isomonodromic deformation. So you're going to preserve the corresponding monodromy representation and only vary the curve. That means that if you have a Z variation of Hodge structure that you start with, then you'll actually stay a Z variation of Hodge structure as you move around.
Stay as Z locus.
Stay as Z locus. Okay. So I think with that, I can state the. So I sort of glossed over it in my definition, but whenever I have this decomposition, or its equivalent to a filtration on this bundle, there's a notion of the length for it, or the level, and I'm going to call that L. Okay. So the theorem is that if a very general isomonodromic deformation of enabla supports a complex variation of Hodge structure of level L on a codimension delta locus in MG, then I can say the following about that delta. The delta, the codimension, is at least G minus R minus L squared minus L. So in particular, that means that if the rank and the length are pretty small relative to the genus, or if the genus is very big, then this is going to be a proper locus. And now this is a statement about complex variations of Hodge structure, applies to a larger class. But in particular, because of what I said about that sort of flatness of these non-abelian Hodge loci, if you actually have a Z variation of Hodge structure, that's really telling you about the codimension of a component of the non-abelian Hodge locus.
I have a question. Back over here, why do you consider VHSs to be more naturally on the Higgs bundle side or the flat bundle side?
Not that I'm critiquing this.
How do you think of this as a natural embedding on the right?
Right. So the reason I said that this is sort of a more natural notion is that one way to characterize variations of Hodge structure is that there's an action by C star on the whole collection. And yeah, so you can characterize variations of Hodge structures at fixed points through that action.
Okay.
I could have defined them just to be flat bundles as well. I just already defined Higgs bundles. So.
Good.
I have a question.
Sure.
Why is the isomodromic deformation of CVHS still CVHS?
Well, that's not necessarily true. So the sort of the content of the theorem is that's kind of baked into the assumption. So if you get that, yeah. So I'll say more about this in a second, but what is true is that there is some sort of like Hodge filtration on the isomonodromic deformation. And you can say something about the rank and of the local system with respect to that deformation, but that filtration may not be the Hodge filtration exactly, but I'll state that more precisely in a second. To also give another result about variations of Hodge structure, although not about the non-abelian Hodge locus, is that again, there's a corresponding monodromy representation, and there's a monodromy group for that. So you can take the image of that representation, you take the Zariski closure of it, the identity component of that. Well, it turns out that the Lie algebra of that is also a variation of Hodge structure. And the same methods that are going to prove this are going to say something about that Lie algebra. So again, when they say E prime nav prime as a very general isomonodromic deformation of enabla. Okay. If P is the algebra of the monodromy group, of E prime, double prime. And in fact, there's the falling bound on the rank of this. So the rank G is at least G minus delta minus the length of the corresponding Hodge filtration you're going to get about this. So I'll say length of filtration. So just to maybe give a feeling for that, the length of a Hodge filtration on this is like L, then the endomorphisms of E is going to be length 2L plus 1. You can increase or decrease the filtration, and this will have some length that is, at most that. Okay.
So theorem A, like L is bounded by R minus 1 or something, right?
That's correct, yeah.
Sorry, what do you call a very general?
Sorry?
What very general mean?
Variation of Hodge structure?
Very general.
I'm sorry, what about the original?
What do you mean by a very general isomorphic?
Oh, very, very general, sorry, I misheard you. I mean analytically, very general. So this is like in the complement of a countable union of closed analytic subsets. So very much hay in a haystack. Okay. So far I've talked about variations of Hodge structure. And that's the main application of these theorems. But as you'll see once we talk a little bit about the proofs of these are going to follow from some analysis of stability of bundles. You take the Hodge filtration and you want to deform that and do some homological algebra to see what happens. And what happens is those bounds show up. But stability is, a pretty general condition. And deforming a filtration is something you can ask about on any bundle. And it turns out that a lot of the content of this first theorem is actually going to be true on any flat vector bundle. The reason for that is a theorem of Simpson. This is the Hodge-like filtration that I alluded to earlier, is that any flat bundle admits a Griffiths transverse filtration. And moreover, let me call that filtration F. Then once I have that filtration, I can take the graded object with respect to that filtration. And that is going to be a Higgs bundle. And that Higgs bundle is going to turn out to be semi-stable. So this is not a unique filtration, but for a variation of Hodge structure, it is going to be. It is because it's the Hodge filtration. But you can actually put this on any flat bundle. It's a very clever construction. I can maybe say a bit about where it comes from. So the kind of goal is to get a semi-stable Higgs bundle at the end. If you want to study semi-stability, the filtration that controls that is the Harder-Narasimhan filtration. So if I have my flat vector bundle, I can consider it as a Higgs bundle, and I can ask whether that's semi-stable or not. If it's not, it has a Harder-Narasimhan filtration. And what Simpson does is he just quotients it out, or rigs it up to be Griffiths transverse. But again, that breaks the semi-stability now, if you kind of combine these pieces of the filtration in weird ways. So what he does is he takes the Harder-Narasimhan filtration of that. He modifies that to be Griffiths transverse and keeps going, proves that you can only do that so many times before you arrive at something that is semi-stable. So I'm going to call that a Simpson filtration. So then I can essentially restate theorem A. But now for any flat vector model. So if the very general isomonodromic deformation of E nabla has a Simpson filtration of level L, then the same rank bound holds. So the rank of E is at least or strictly greater than actually square root of G minus the level. That's the level. You can also, if you want to talk about if on a particular locus the length of that filtration is actually L, and maybe on a different locus the length is slightly different, you can incorporate the codimension as well to kind of break that up. But as I said before, the Simpson filtration exists on any flat vector bundle, so I can talk about the most general deformation that's going to go to all of MG. So any questions so far? The statements of the theorems?
Sorry, I'm looking, what happens if E is like rank 2 or something? Have this very general isomonodromic deformation, right?
Thus,
That's gonna have some Simpson filtration. If your inequality is going to break, no? Because the right hand side is like bounded by root G from below or something, right? So isn't that just, am I confused? Is that saying rank E is always bigger than root G?
okay, I might have to be a little careful in the low rank case.
Okay, there's some
Well-
assumption like E is big enough rank or something?
Sorry, there's another
Sorry,
one.
sorry, no, so there's some assumption about E having big enough rank for this to be.
Well, the assumption I should make is that G is at least 2 as well, and yeah, probably the rank is also going to be greater than 2.
I think maybe it's, you want L bigger than 0 or something?
Oh, yeah, the length. Sorry, I am assuming that the length is positive here.
No, but sorry, the right hand side is just bigger than root G, right? No matter what.
No, but this inequality only applies when L is bigger than 0.
Oh, so most guys of low rank will have L equal to 0, is that the point?
Yeah, perhaps the next thing I want to say might shed some light on it, which is kind of the original motivation for this theorem C has to do with these techniques were actually first used to tackle a different problem, which is whether or not vector bundle is semi-stable in this isomonodromic deformation. So let's say that. Right. Okay.
Yes, I think also over here, these statements are for L bigger than 0.
Yeah, sorry, that was, yeah, I sort of implicitly assumed that in every case. So the remark perhaps is that length greater than 0 implies that E is not semi-stable. The reason for that is that the deepest piece of the Hodge filtration or the Simpson filtration is going to be destabilizing. And I can rephrase this theorem in the following way, which is that so if the rank is less than root G, it's 1 plus 1, any non-trivial filtration, then the isomonodromic deformation would have to be semi-stable. That's the general isomonodromic deformation is semi-stable. So that's what was originally the question attacked by Landesman-Litt. Just for comparison, for the same statement, their bound is 2 square root of g plus 1. So this is not quite as good as that bound. The reason for the discrepancy is basically kind of some clever stuff you can do with AMGM. You talk about having many pieces of a Hardner-Osmond filtration, whereas the method of proof for this is not going to isolate many different pieces of the filtration. Okay. Perhaps another remark is that much of this is going to remain valid in the setting of curves with punctures. So much of this works in the non-compact setting. The object that you're working with in that case is going to be a flat bundle with regular singularities. So these can be parameterized by this moduli space of logarithmic vector bundles. And under a couple of assumptions that I'll just say, under a resonance condition on the connection and under some assumptions about the stability of the underlying bundle, you can restate all these theorems for variation of Hodge structure or for flat vector bundles in the non-compact case. Perhaps another remark to make is that the way I've stated things so far is I'm kind of talking about, I have a curve in MG and I want to deform that to this flat vector bundle that exists over all of MG. But this statement is really about a foliation that's happening on this relative to Rham space. So that isomonodromic deformation construction actually produces a foliation where each leaf is isomorphic to a copy of Teichmüller space. And so these bounds, more naturally maybe, are bounds on the intersections of the non-abelian Hodge loci with leaves of that foliation. Okay. So I get a bit into the details of the proofs of these theorems. So there were 3 theorems. There was the one, there was the Codimension bound for variations of Hodge structure. There was that rank bound for flat vector bundles, and that one will clearly imply the bound for variations of Hodge structure. Then there's also this Lie algebra, and I might not get to the proof of the Lie algebra bound, but I'll have a word to say about it at the end. I'm mainly going to concentrate on the first 2 theorems I said. So the point is, we have our vector bundle, and how do we parameterize infinitesimal deformations of the vector bundle? Well, that's with the H1 of the endomorphisms of the vector bundle, whereas parameterizing deformations of a curve is H1 of the tangent bundle. And Atiyah, in his paper on connections, kind of give a way to relate those 2 objects. So he constructs a bundle of differential operators on your curve. And one way to think about a connection is that it's a certain splitting of this sequence. And you can think about that, okay, well, H1 of this sequence is going to be exact on H1 for curves. And so I have the deformation space of my curve, I have the deformation space of the flat vector bundle. In some way, homologically, The connection will also give me some information about the deformations of the pair of those two. I won't do the entire diagram case, but the output of the assumptions is we're assuming that the flat vector module with its Simpson filtration deforms to some codimension delta locus within MG. That's going to produce a map, this connection, from the tangent model of the curve to the endomorphisms of E. And in fact, it's going to go to endomorphisms of E that break the Simpson filtration. And moreover, the assumption about where this happens is that this map has delta dimensional image on first homology. But we're deforming the Simpson filtration. And the whole point of a Simpson filtration is that it's going to be Griffith's transverse. And Griffith's transversality means that, okay, well, it doesn't just break the filtration, it breaks it by precisely one piece. So Griffith's transversality is going to imply that this map actually, or rather, induces a map to specifically those endomorphisms of E that break the filtration by precisely one piece. Okay, and this is maybe a different way of writing it, but this is essentially the Higgs field that's on the endomorphisms of E. Okay, so now let me consider the Serre dual of this map. So Serre duality. Take the Serre dual. And this is now endomorphism. The source is going to be endomorphisms of E that raise the filtration by one piece. Tensored by omega to the quadratic differentials. C. Okay. And whereas this map, you can show that once I do this reduction, it still has the same rank on H1. This is going to have that same rank on H naught. So this is rank delta, really at most delta on H naught. Okay.
Sorry, what do you mean rank? Rank, what kind of rank?
Or the image of the map on H naught. The dimension of that, like within that vector space. I see. Okay. Okay. Well, I mentioned you can view that as the Higgs field on NP. On the other hand, I can write down the Higgs field on specific piece of the endomorphisms of E is, well, the Higgs field is particularly given by bracketing with theta. If I take an endomorphism that raises the degree of my filtration by 2, and the Higgs field drops the degree by 1, then now I'm going to get a 1 form valued with an endomorphism that raises the degree only by 1. But the defining condition of a Higgs field is this integrability. So that's a Higgs field here. This is a Higgs field here. I compose the two, I have to vanish. So in particular, that means this Serre dual map is actually factoring through the image of this. So psi Serre dual factors through the image of this. I should say the co-kernel. Like plot Q, this map. Okay. So really what I have is another map, and let me call it var P now. And again, with some diagram tracing, you can show that the same condition on the rank of the image on H naught is going to be the same. It's still at most delta dimensional on H naught. Okay. So now let me make an assumption that's actually false. So suppose that this is semi-stable. So suppose that Q is semi-stable. This is not true. I have no reason to believe this is true. But what you can do is you can do some more reductions to eventually isolate a semi-stable bundle that has a non-zero map to omega squared with the same property. It's just that doing that and also handling how that works in the non-compact setting is maybe most of the technical meat of the proof. So I'm just going to sidestep that and assume it.
Just back here, where did that big dimensionality come from? Maybe you mentioned about it, but I think I missed it.
Right, I only said in words, and it is a bit of a diagram trace, but
What is word is it? Because this comes from delta is the codimension on the moduli space, right?
right. So basically, you have this filtration or this exact sequence, and there's a similar exact sequence for when you have a filtration. And if you compare those two, that's where this map comes from.
Okay.
And in the kind of large diagram of comparing the two, if the filtration happens to deform in the same locus at which the vector bundle deforms, then one of these maps in the long exact sequence of that, the long exact sequence you get in cohomology is going to vanish. So basically, the locus at which the filtration does deform, the dimension of that is going to be in the kernel of a connecting map in the long exact sequence. And so the image you get in the next map over is going to be delta.
Okay, so this somehow is related to measuring the deformation of the filtration in some way.
That's right.
Okay, well, one way to say it is that this map on H1 is the obstruction map to deforming the Simpson filtration in the isomonodromic deformation.
I see. Okay, cool.
So yeah. Right. So we have the semi-stable bundle. And one thing I haven't said yet or used yet is, well, what are the slope properties of that? This Q is a quotient of this GER1 and E tensor omega. That itself is a bundle, that's itself is a quotient of just the endomorphisms of E. Endomorphisms of E has degree 0, and omega has degree 2g minus 1. And so the stability of the Simpson filtration gives you that this quotient has to have slope at least or strictly greater than actually 2g minus 2. So that's what we're going to use for this analysis. So let me take the kernel of this map. Kernel of this bar P. That's going to be at least the H naught of Q minus delta. And Riemann Roch is going to say that is at least the rank of Q times the slope plus 1 minus the genus minus this delta. On the other hand, there's Clifford's theorem for vector bundles that happens to apply in this case. So Clifford's theorem says that the H naught of the kernel is going to be at most the degree over 2 plus the rank. But using that semi-stability hypothesis, that's going to be at most the slope of Q times the rank of Q minus 1. The kernel has to be proper because this map is non-zero. Divided by 2 plus the rank of Q minus 1. Okay. So this quantity here has to be larger than this quantity here. At this point, you just solve. And so simplifying, you get precisely that the rank of Q is going to be greater than G minus delta. This is a quotient of endomorphisms of E, GER 1. So omega. So the same bound is going to be true for just the rank of this. And I should just say that this type of argument here is called like a non-GGG lemma. Non-GGG argument. Used by Litt and Aaron Landesman for studying kind of generic global generation of bundles using in kind of a similar setup to this. Okay. So we're not quite done. That's a bound on the rank of the, a specific graded piece of endomorphisms of E. I have to go from that to actual bound on the rank of E. And the way we're going to do that is AMGM. So if I can write the rank of E, the rank of, let me say the GER 1 of NE as the sum of the consecutive ranks of the graded pieces, the ranks of the consecutive graded pieces. Okay. Well, the AMGM inequality says that this sum is bounded above by the rank of this sum squared divided by 4. Cauchy-Schwarz form of it is going to say that this term can be bounded above by half the squares of the consecutive sums. Okay. Well, I sum that up. At the tail ends, I'm going to have just half of a square of a rank. Everywhere else, I have one copy. So this is at most the sum from 0 to L of the rank of each graded piece squared. Okay. Well, how big can this be? You can do just a little smoothing argument to show that the rank of this has to be is going to be the largest when you concentrate as much of the rank you can at just one graded piece, and everything else just has rank 1. The way that works out is that rank is going to be greater than the rank of the vector bundle minus the length squared, plus the length. This is where this is like L1 squareds. Yeah. So that ends up being where the bound on the rank of E comes from. Because again, it was G minus delta that this inequality satisfies. And then you can solve for the codimension as well to get the same thing.
Right. So ask a question. So I guess you get a much better bound if you're willing to assume include within your data more than just the depth of the Simpson filtration, but also the actual dimensions of the graded pieces.
Right. Yeah. Mm-hmm. You would get something stronger. Yeah, for sure. So that is the proof of the first theorem and the third theorem I stated. In the remaining time, I'll just say a little bit about that middle theorem about the monodromy group.
Can you do even, this is also just throwing it in the front, can you do better if you assume the extreme case? That seems quite constraining on your guys, right? Because it's a bunch of like degree 1 guys, not the degree 1 guys under the Higgs bundle.
Right. Yeah, there's probably some more work to be done on optimizing that bound. I haven't done too much with it.
Are there any extremal cases of particular interest? Studied?
Not of particular examples that I know. No. I can just say it as an aside that the possible Simpson filtrations are kind of unknown in general. I think Hengfei Huang has done all the rank 3 Simpson filtrations, and so perhaps you can compare how optimal that is versus all the ones that exist in rank 3. But the complexity of computing it by hand just grows
Sure.
enormously, so I couldn't say much about higher rank.
You're never getting anything beyond codimension. I mean, this is very impressive already. You're never getting anything beyond codimension G.
Right.
Is there like a true, like the method gives this, but is there a true reason for that? Like, does something just happen beyond codimension G that you can show you have these families of deformations that?
No, I don't know the particular examples. I guess the lead I have, but haven't investigated, I confess, is that the hyperelliptic locus is about that codimension, and so weird things tend to happen with that. So for him, potentially that could be something to look into. Right. So let me just briefly blurb about the theorem about the rank of algebraic monodromy group. The point is that when I deform the connection, then the endomorphisms of E also have their own Hodge structure. And in fact, I don't know of a simple proof of this, but the Lie algebra monodromy group is a sub-Hodge structure of these endomorphisms of E. So if I can just erase here, when I get a map like this, I'm just as well going to get a map to the monodromy, the Lie algebra monodromy group modulo those endomorphisms that preserve the filtration there. And this is a degrees of the flat vector bundle. And so all the stability properties that go through with the rest of the proof are going to apply to this as well. And so you can just replace the endomorphisms of E with this object and run the rest of the proof through, and the same numerics all work out. And that produces the rank bound for this object. You play the same trick with going from just the the first graded piece of that to adding all the other pieces of the filtration, just 1, 1, 1, 1. Are there any questions? Okay, well, thank you for your time.